Hi all, welcome to the lecture series on Aerospace Propulsion. Myself, Mr. Manideep Gupta, Assistant Professor, Department of Aeronautical Engineering from MLR Institute of Technology. Today, the topic which we are going to discuss is about cryogenic propellants. So, coming to the propellants which are used in the aerospace applications, cryogenic propellants plays very important role in space applications. Okay, so we are going to discuss about the cryogenic propellants in this lecture. Coming to the overview of today's presentation, the topics which are going to be covered in this lecture are fundamentals of cryogenics and the components in cryogenic systems, cryogenic fuels, cryogenic propellants, and safety aspects to be considered in cryogenic systems, basic cryomodule design considerations, and next generation cryogenic engines. These are the topics are going to be covered in this lecture. Coming to the first one, fundamentals of cryogenics and components. What is cryogenics? Okay, what is cryogenic? Cryogenic is the study and use of materials at very low temperatures, typically below minus 150 degrees centigrade. So, in cryogenics, the cryogenics studies about the materials. It studies about the materials behavior at a very low temperature. At a very low temperatures, typically below minus 150 degrees centigrade. If you consider in the terms of kelvins, it will be 123 Kelvin. So it involves in understanding how materials behave at the extreme conditions. The cryogenic deals with the behavior of a different materials at extreme conditions, that is low temperatures. And we do research and we apply those materials based upon the behavior for our applications. And extreme conditions and design systems to produce, maintain and use such low temperatures. So cryogenics deals with the behavior of a different materials at extreme conditions like low temperatures and maintenance and applications of different materials at low temperatures. Right. Coming to the fundamentals of cryogenics, it basically involves thermodynamics at low temperatures, the thermodynamic behavior or thermodynamic properties of a system at low temperatures. And because at the low temperature, the properties of material, we have to go through the properties of material, like material properties at low temperatures, and the process of maintaining material at low temperatures, and we have to go through the superconductivity. Okay, at cryogenic temperature, some materials possess superconductivity, so we have to deal with that property, and maintaining heat loss, reducing the heat loss. Okay, the concept of reducing heat loss, that is vacuum insulation, should be also comes under while dealing with cryogenic systems. Okay, coming to thermodynamics at low temperatures. So heat transfer mechanism, we should go through the heat transfer mechanisms like conduction, convection and radiation, how behave differently in cryogenic temperatures. And thermodynamic cycles like Joule-Thomson cycle, Brayton, Claude cycle are used for cooling of the materials to a low temperatures. Okay, so we have to go through this heat transfer methods. So all those, right? Material properties. Coming to the material properties, the materials become brittle. Generally, materials become brittle or superconducting at cryogenic temperature, that is at low temperature. So we should go through the property, what is the brittleness and the conducting nature of a particular material, whether it is suitable for our application or not. Next, thermal contraction. Thermal contraction is also very important. It is significant that must be managed. The thermal contraction must be managed. Right? Any material, if you heat it, okay, some materials generally, if you heat it, they will get expand, right? So the volume of the material increases, and if you cool the material, it will if it is in liquid state, while it converts to solid state, the contraction happens, the volume will decrease, so shrinkage will be there. So material thermal contraction also to be considered for a particular material, comparing at room temperatures and also at low temperatures. That should be also managed. The thermal contraction should also be managed for cryogenic materials used for cryogenic systems. Next, liquefaction of gases. Okay, in cryogenics, generally we liquefy the gases. Okay, the gases at room temp, the gases, okay, at room temperature, they possess a gaseous nature, right? So when you cool the gases to a very low temperatures, it will convert to the liquid state. The gases will convert to the liquid state. That process is nothing but called liquefaction of the gases. So cryogenics often involves liquefying gases. We liquefy the gases, we decrease the temperature, and we may convert the gases into liquid state, such as nitrogen, liquid nitrogen, oxygen into liquid oxygen, helium. Okay, so this liquefaction process also has to be monitored. Okay, for different gases, right? And requires multi-stage compression. For this liquefaction process, we need a multi-stage compression, and processing like a pre-cooling stages are required for liquefaction of gases. And coming to superconductivity, at cryogenic temperatures, certain materials, not all materials, certain materials exhibit zero electrical resistance. Zero electrical resistance. So it is superconductivity. The electricity flows freely without any resistance. So it is sometimes this superconductivity, uh, we have to take some measures to avoid, to make insulations for other supporting systems when the material behaves as a superconductor. Insulation must be done properly, and so for that we have to study about the vacuum insulation also. Okay, vacuum insulation is also very important. Insulation generally reduces the energy transfer, and maintains the materials at required temperatures. Heat losses will be decreases by insulation. So vacuum insulation to minimize the heat transfer, and in cryogenic systems often we use high vacuum insulation and multi-layer insulation. We can use both concepts, vacuum insulation and also multi-layer insulation is used in cryogenic systems to avoid heat transfer from the system to the surroundings. Okay, coming to the components of cryogenic systems. Components of cryogenic system. The main components of cryogenic systems are listed here: cryocooler, flask, cryostat, vacuum jacket, heat exchangers, expansion valves, pumps and compressors, transfer lines, sensors and controls, shielding. All these are the basic or major components in cryogenic systems. Okay, so we'll go through the functions of each component here. So cryocooler. Okay, the cryocooler is used for refrigeration unit. It is a refrigeration unit that achieves cryogenic temperatures. Okay, so cryocooler helps to cool the materials to a low temperature or required temperature. Okay, it is a process of, if it is a refrigeration process. Next, cryostat. Okay, it is a container. Cryostat is a container for storing cryogenic fluids. So cryostat has specific features. It will be thermally insulated. It will insulation layer will be there for the particular container to reduce the heat losses. So cryostat is a container for storing the cryogenic fluids. So we cannot store cryogenic fluids in normal containers. If you store in normal container, there is a easy energy transfer happens from the surroundings and the cryogenic liquids, and icing happens. Okay, so we have to store these cryogenic liquids at special containers which are called as cryostats. Next, vacuum jacket. Okay, this cryostat will have an insulated outer layer to reduce the heat in leak. Heat leak will be reduced with the help of this vacuum jacket. We discussed, right, vacuum insulation. So vacuum jacket is a component in vacuum insulation. Next, heat exchanger. Next one is heat exchanger. It improves the efficiency by exchanging heat between fluids. It will maintain a constant temperature. Even though we go for any whatever the insulation you go for, there will be a heat loss will be there. In practical conditions, there will be some heat loss occurs. Okay, and expansion of the fluids occurs. So what we do is we place heat exchangers to maintain a constant temperature or to maintain a substance at a required temperatures. Heat exchangers maintain uniform temperature throughout the liquids. Next, expansion valves. Okay, so these are used in Joule-Thomson cooling for pressure reduction. Okay, whenever there is some expansion happens due to the heat leak while increasing the temperature of substance, so the pressure will increase. So in order to reduce the container pressure, even we should go for a pressure releasing valve sometimes. Otherwise, if the pressure builds high pressure builds in the container, it may lead to a failure of a container. Okay, right? So expansion valves used here, the expansion valves used in Joule-Thomson cooling for pressure reduction. And next, pumps and compressors. Pumps and compressors generally move and compress gases for liquefaction. Okay, and next, transfer lines, special piping system. These are special pipes to transport cryogenic fluids from container to the combustion chamber or required places. So transfer lines are also major component. These transfer lines also needs insulation, uh, insulation, so that while transferring the liquid, cryogenic liquids from tank or cryostats to the combustion chamber or required place, even heat losses will be there. So insulation is also done for transfer lines. So special pipes are used for as a transfer lines in cryogenic systems. Next, sensors and controls. These are very important component which will give us the real-time data about the cryogenic system. So we can monitor and regulate the pressure, temperature, and flow of cryogenic liquids, heat flow, or else all data can be maintained with the help of sensors and controls. Next one is shielding. So which will reduce the radiative heat transfer. Okay, only with multi-layer insulation or cold shields. Okay, shielding is reduce the radiative heat transfer when in a multi-layer insulation or cold shields is used. So this is about the introduction about the components, different components in cryogenic system and their function. Right? Cryocooler is used as a refrigeration. It decreases the temperature. Cryostat stores the cryogenic propellants. Vacuum jacket, it reduces the heat transfer. Heat exchangers maintain uniform temperature over the cryogenic fluids. Expansion valves used in Joule-Thomson cooling for pressure reduction. Pumps and compressors. Pumps will transfer cryogenic liquid from one place to another place. Compressors will reduce the temperature or increase the pressure so that it will convert into liquid. Transfer lines use it to transfer one place to another place, and sensors and controls will give us the real-time data so that we can control the parameters. And shielding is reduce the radiative heat transfer. So these are the major components of cryogenic systems and their functions. Next, common cryogenic fluids. Common cryogenic fluids. Okay, the cryogenic fluids, you can see here: liquid nitrogen, liquid oxygen, liquid helium, liquid hydrogen, liquid nitrogen tetroxide N2O4, and liquid methane CH4. These are all the general common cryogenic fluids which are using now. Okay, coming to this, the boiling points. Okay, liquid nitrogen, the boiling point is 77 Kelvin. Okay, it is used for food freezing and preservation and superconductors. Liquid nitrogen is used for food freezing, preservation and superconductors. The boiling point is 77 Kelvin. Next, liquid oxygen. Here the boiling point means generally liquid turns to gas at a boiling point, right? So you can in liquefaction we can consider this as a liquefaction, like a melting point also. Melting point is some solid to liquid, right? So boiling point, so liquid to gases or gases to liquid. Okay, at 77 Kelvin, nitrogen will turns to liquid nitrogen, right? liquid oxygen, the boiling point is 90 Kelvin. We use this liquid oxygen as a aerospace propellant, okay, aerospace oxidizer. So we use rocket oxidizer, and even medical breathing gas, even medical breathing as a medical breathing gas also we are using this liquid oxygen. Next, liquid helium. The temperature is boiling temperature is 4.2 Kelvin. It is very less. Okay, 4.2 Kelvin for superconductivity and MRI cooling. For these applications, we use liquid helium. Next, liquid nitrogen tetroxide, 294 Kelvin. The boiling point is 294 Kelvin. That is 21 degrees centigrade. But it is not actually cryogenic, but it is a liquefied gas. Okay, it is a liquefied gas. So it is used as a oxidizer and storable hypergolic nature. Okay, and next, liquid methane, it is minus 161 degrees centigrade, that is 112 Kelvin. So it is a fuel. It is a generally we use this liquid methane as a fuel. Increasing, like the popularity of liquid using liquid methane is increasing day by day. Next, cryogenic. So this is about the cryogenic fluids and their boiling points and their uses. Okay, cryogenic propellants are fuels and oxidizers stored at very low temperatures. Coming to the cryogenic propellants, cryogenic fluids. Okay, what is cryogenic propellants? Cryogenic propellants are nothing but the cryogenic fluids which are used as a propellants, right? These fuels and oxidizers are stored at very low temperatures to keep them in liquid form. So they are widely used in rocketry. Mostly these cryogenic propellants are used in rocket space applications, space launch vehicles, because of their high efficiency and energy content. The cryogenic fluids has high efficiency, and the energy content stored in the cryogenic propellants is high, because generally the volume of gas will be this much, but when you convert this into liquid, the volume decreases to this much. So the storage space also reduces for cryogenic liquids. Okay, and structural mass also decreases, but even though we have to use cryogenic systems, separate cryogenic systems, but the space occupied by the propellant will reduce, and the efficiency also high for this cryogenic fluids. That's why we are using cryogenic propellants for space applications, and even at launch vehicles also we are using this cryogenic propellants. So coming to the common rocket propellant combinations. Propellant is a mixture of oxidizer and fuel, right? Propellant is a mixture of oxidizer and fuel. So in this, the different combinations can be used as a propellant. Different fuel and oxidizer combinations can be used as a propellant. So coming to the combinations of rocket propellant combination. Okay, for rocket propellants. So fuel and oxidizer. Okay, liquid hydrogen and liquid oxygen. These are used in space shuttle, already used in Ariane and Delta 4. Okay, liquid hydrogen plus liquid oxygen as a propellant combination. Next, liquid methane plus liquid oxygen. This is used in SpaceX Starship. It is used in SpaceX Starship, Blue Origin, New Glenn. Okay, and coming to the RP1, kerosene plus liquid oxygen. It is liquid oxygen is a cryogenic, but kerosene is not cryogenic. So we can say this is a semi-cryogenic propellant. It is semi-cryogenic propellant. So it is not cryogenic but semi-cryogenic, but often used for comparison. Right. Next, hypergolic. We are using this combination also in space applications. Next, hypergolics like MMH and N2O4. Okay, oxidizer is not available. Stored at room temperatures, ignite on contact. So hypergolic propellants means generally when they react spontaneously. They react spontaneously. No need of any ignition system is required. So these are comes under hypergolic, like MMH with N2O4, and comes under hypergolic one. Okay. Next, cryogenic safety aspects. Handling cryogenic materials involves unique risk due to the extreme low temperatures. We already discussed, right? Cryogenic itself means at low temperature, maintaining material at deals with low temperatures. So there is a high risk. Okay, different challenges comes when you have to maintain a material at a very low temperature. So the properties of fluids here are their key considerations. Okay, safety aspects are very important for maintaining cryogenic systems. Okay, because extreme cold condition will be there, acidification will be there, pressure buildup will be there. Okay, what happens? So extreme cold condition, this can cause severe frostbite and cold burns and tissue damages. When we expose to this extreme low temperatures, it can cause severe frostbite, cold burns, and tissue damage. So, for example, the skin contact with liquid nitrogen or cold surfaces, we can feel these sensations. Next, asphyxiation, asphyxiation. So here, displacement of oxygen in the air due to the evaporating gases. Displacement of oxygen in air due to the evaporating of gases is called asphyxiation. Okay. So leak of nitrogen gas in confined spaces, reducing oxygen levels. So when the liquid nitrogen leaks, okay, so the oxygen content, the nitrogen percent increases and the oxygen level decreases. The proportion of oxygen in air decreases. So this will cause of asphyxiation. Right. Next, pressure buildup. Cryogenic liquids generally vaporize rapidly if the temperature is not maintained constant. Continuous monitoring is required. So, if any variation in temperature, they will expand. Then the pressure will be build up. Pressure increase happens in the cryostats. So, causing high pressures in the containers or even in pipings also while transferring liquid from one place to another. If there is any heat loss, they will expand and pressure builds in the cryogenics. So it is also one of the very important safety aspects to be considered. Pressure buildup is a very important, which can leads to the complete failure of cryogenic system. So tank rupture if pressure relief fails. Okay, so these are the safety aspects to be considered, and flammability and explosion. So easily catches fire, contains high energy content. Cryogenic fluids contains high energy. So we have to maintain, we have to control this flammability and explosion safety aspects. Okay, some cryogens like a liquid hydrogen, liquid methane are highly flammable and explosive in air. So we have to control the mass flow rate very keenly. Okay, keenly we have to control the flow rate so that excess injection will lead to the explosion. Okay, hydrogen leaks mixing with the air causing fire and explosion risk is there. Next, material embrittlement. So material property, the material may become brittle and it may not sustain high pressures sometimes at a low temperature. So we have to take care of that also. We have to control the we have to monitor, have to analyze the proper behavior of a material at a low temperature. So like metals and materials become brittle and can fracture at low temperatures. So we should be aware about the materials limits of usage of a particular material for while using for any applications, so that this material embrittlement can be controlled. So cracking of piping or vessels under stress can happen because of this brittleness nature. Okay, at cryogenic low temperatures the pressure will be more and the container brittleness increases. So the strength of container is a very important factor to store safely. So that's why these are the very important considerations to be taken as a safety aspects. So what are the safety measures and best practices to be taken while maintaining the cryogenic systems? Coming to the safety measures and best practices. Okay, so personal protective equipment. Okay, personal protective equipment. So we have to use cryogenic gloves, have to use face shields, aprons, and safety glasses as a personal protective equipment to avoid the direct contact of a high cold sensation. Next, ventilation. Proper ventilation to be maintained. ensure good ventilation to prevent oxygen displacement and accumulation of gases. Okay, ventilation to be maintained properly, even though some nitrogen and any gas leaks, so it should not decrease the decrease the percentage of oxygen in the air mixture. Okay, so ventilation has to be maintained. Next, pressure relief devices. Pressure relief devices to be maintained for cryostats. So equip vessels with pressure relief valves to prevent over pressurization. Right, the pressurization of the tank can be maintained with the help of this pressure relief devices. If the pressure increases, we can use these devices and reduce the pressure immediately, even though we cannot, if you are not able to maintain temperature immediately, we can release the pressure and we can maintain the safety of the cryostat. Next, proper storage. Use highly insulated dewar flask or cryostats with vacuum jackets to minimize the heat influx and boil off. So proper storage, like the cryostat design, the vacuum insulation, everything should be perfect. Okay, so that the heat loss will be less. Next, handling procedures. So we should avoid direct contact with cryogenic liquids and cold surfaces. Use proper transfer techniques. We should use a proper transfer techniques while transferring liquids from one place to another place. We should not go for direct contact, which will lead to a cold burn or it will gives skin problems. Leak detection systems is must for as a safety measure. You have to use sensors for flammable gases and oxygen deficiency monitors also to be maintained to address the problems of a leak. Okay, leak detection has to be is one of the uh, safety measure to avoid oxygen displacement and to detect the flammable gases. Next, material selection. Material selection is one of the key parameter for maintaining the safety of a cryostat. So we have to use materials compatible with cryogenic temperatures for a particular liquid to prevent brittleness of a material. So this is also one of the safety measures. And next, training and signage, like train personnel on cryogenic hazards and emergency response, post warning signs, everything. The training, the whoever the personnel dealing with cryogenics, they should be well trained so that there should not be any mistake goes and the safety will be maintained properly. So these are the safety measures and best practices. Next, cryo module design considerations. Okay, everything is interlinked, right? Safety measures. So while designing, while going for design considerations, we should go for safety measures. Whatever the safety measures are required, according to that, we should go for design. And also, we have to we have to concentrate on the requirements, the temperature or pressure, the parameters has to be maintained. All this has to be managed while designing the cryo module. So the thermal insulation should be perfect, will minimize heat load and maintain low temperatures. Use vacuum jackets and multi-layer insulations to reduce the thermal insulation. And mechanical support like support SRF cavities without causing thermal conduction or mechanical stress. Use low thermal conductivity materials like a G10 fiberglasses, which will which can have low brittleness at low temperature. Cryogenic flow management. So efficient routing and liquid helium or other cryogens to cool cavities uniformly, minimize pressure drops. So flow management also is a very important in a cryogenic design consideration. Next, alignment and stability and magnetic shielding, thermal shielding, magnetic shielding, and electric shielding. Everything to be shielding is a very important, right? So precise alignment of cavities, micrometer accuracy, minimize vibration and thermal contraction effects, and for alignment and stability, these are to be considered. And magnetic shielding protect cavities from ambient magnetic fields that degrade superconductivity. Use mu metal and cryogenic magnetic shields for this purposes. So these are the key design considerations like thermal insulation, mechanical supports, cryogenic flow management, and alignment and stability, magnetic shielding, and thermal insulation already came, right? So these are the things. And next, vacuum system for insulation process. And next, thermal contraction and accommodation, instrumentation and sensors monitoring the system, access maintenance and safety features. So these are all the things which comes under cryogenic module design considerations. So vacuum installation, maintain ultra high vacuum around cavities to avoid contamination of RF losses, and thermal contraction. Use bellows flexible supports, okay, for avoiding contraction to work to address the contraction. Sliding components to handle differential contraction between materials. So, okay, different materials will have different expansion rate, right? So that the level of contraction varies. So differential contraction can be handled with the sliding components, and instrumentation and sensors, temperature sensors, pressure gauges, and RF monitors for system diagnostics and control. These are proper supportive sensors has to be placed in the cryo system so that they can work efficiently at low temperatures also. Next, maintenance. Modular design for easy assembly, maintenance, inspection, and repair. So the design should be such that assembly should be easy, and easy inspection and maintenance. Next, safety measures like a pressure relief valves to be maintained, vent lines, emergency shutdown systems, okay, proper heat flow management systems. All this comes under safety features. The design consideration comes under safety features. So this is about the cryo module design considerations. And next, coming to the last one is a next generation cryogenic engines. So even though we are using cryogenics, still there is something to be developed, and which we have to address. Okay, so coming to the choice of fuels, so use of fluid methane. So alongside or instead of hydrogen for easier storage and handling, like a higher density and better reusability. So we have to focus on usage of liquid methane as a cryogenic fluid for a next generation cryogenic engines. And next, reusable designs. We should go for reusable designs, like engines designed for multiple flights, okay, with a minimal refurbishment, minimum maintenance. Example, SpaceX Raptor, Blue Origin BE4. Okay, so these are the next generation cryogenic engines, right? Next, fuel flow staged combustion cycle, FFSCC. Both fuel and oxidizer are fully gasified and burned in turbines before injection, increasing efficiency, reducing thermal stress, and enhancing reliability. So instead of using direct liquid cryogenics, we can convert liquid. We can gasify the liquid gases. Okay, we can turn the liquid gases into gases instead, and then we can use so that we can avoid thermal stresses. So the reliability also increases. So this can be done with the use of turbines or before injecting into the combustion chambers. So this is also the concept of next generation cryogenic engines. Coming to the summary of today's topic. So we have gone through the fundamentals of cryogenics. What is cryogenic and the different components in cryogenic system. We have gone through the cryogenic fuels and also cryogenic propellant combinations, different oxygen propellant combinations. Next, we have gone through the cryogenic safety aspects, cryo module design considerations, and discussed next generation cryogenic engines. Uh, so these are the things covered in this lecture. Thank you.